Hello, today I am going to discuss about gusset plates, lug angles and tension splices. These three additional members which is required in case of design of tension members. These three members are used in various reasons which I will discuss today, and how to design all those we will be going through some examples so that it will be clear. Now first, as we know about gusset plate. In fact, already we have discussed about gusset plate in earlier lectures, so we do not need to introduce this term gusset plate. A gusset plate basically is an extra plate which needs to introduce when a joint is consisting of more than one members. That means when a truss like structures where more than one members are meeting in a joint, in that case to make the joint properly, to make the load at a particular point in a proper position, then we need to introduce gusset plate. So this gusset plate has been discussed, means about the gusset plate has been told in clause 8.5 of IS 800. So in the clause it has told that gusset plates shall be designed to resist the shear, direct and flexural stresses acting on the weakest or critical section. So we need to design the gusset plate because of to resist the shear, direct and flexural stresses. And as we told that gusset plates are provided to make connections at the places where more than one member is to be joined. That means joint of trusses, truss girders, etc. So as we see how it look like, let us see that when suppose one truss member is inclined here, another truss member is suppose are placed like this, maybe another truss member is placed like this. So and also say suppose one bottom chord is there. So this is another truss member. Now so these truss members say 1, 2, 3 and 4 are to be joined in this joint. So what we will do, we have to make the connections in such a way that all the CG of the load passes through a particular point. So maybe the rivet line will be like this. So rivets are placed in such a way that the load on the joint is coming through its CG. So this is the gusset plate which we need to say like this. Like this. So this is basically gusset plate. So the function of gusset plate is just to hold the different members in proper position so that the load are being transferred properly from one member to another member through the joint. This is the joint where we have to make the connections properly. So this is the gusset plate. Now so regarding gusset plate I will not discuss much because as already we are familiar with this term gusset plate, and whenever we are going for designing such type of connections we generally use gusset plates. And gusset plates in fact we have to design in such a way that it should be able to resist shear, direct and flexural stresses. So all these things we have to keep in mind. Another additional members which is required sometimes is called lug angles. What is lug angle? Lug angle is basically a short length of an angle section used at a joint to connect the outstanding leg of a member. Basically this is required when the length of gusset plate is limited. When the length of gusset plate is limited, then to transfer the load to connect the joint properly we need lug angle, which is an extra material, extra plate type of things which is required. This is basically in picture whatever we are seeing, this is basically lug angle. So lug angle basically connect, means this is a riveted or bolted joint, means this is another joint. So this is main member, this angle section is main member. So main member is connected with lug angle through the rivets, and rivets the main member also is connected with this gusset plate, as well as the lug angle is connected with the gusset plate. So in this way the joints are made and the forces are being transferred. So we will see how to design the lug angle, and before going to design we will see what are the aspects of lug angle in terms of codal provisions. And before going to codal provision, let us know some advantage and disadvantages of using of lug angles. Basically we can see that using lug angles one can save the gusset plate materials. So one can save the gusset plate material by the use of lug angle. However, extra materials will be required for lug angles and their connections. So when we are going to save the gusset plate materials, we have to provide some lug angle, and in that case for lug angle, for providing lug angle, another set of materials should be required. So means it is balancing, basically balancing means in terms of materials. So if we have the restriction of gusset plates, then we can go for lug angle. Another things we should remember, that is lug angle are not efficient to transmit loads. This is very important. Lug angles are not efficient to transmit loads. Moreover, an eccentricity develops between the load and the CG of the rivet group. Eccentricity develop between the load and the CG of the rivet groups, because this is the load and CG of the rivet groups is will be different. So a small eccentricity will develop. So this is disadvantage, you can say, and therefore generally lug angle is not suitable, means not advisable to use. However, lug angle is generally used at the beginning of a joint, so that it can be effective in sharing load. It can be effective in sharing loads. So lug angle generally we use at the beginning of a joint, so that it can be effective in sharing the loads. However, it is not efficient on transferring the load. So and also it develops some sort of eccentricity between load and the CG of the rivet group. So generally, unless it is very much required, we generally avoid this. Now let us come to the codal provisions. In IS 800 1984, in clause 8.8, some provisions has been given about the lug angle. So while going for designing of lug angle, we have to remember this clause, means this codal provisions which is given in the clause 8.8. What is those? Let us see one by one. First is, in the case of an angle members, the lug angles and their connections to the gusset or other supporting members shall be capable of developing a strength not less than 20% in excess of the force in the outstanding leg of the angle, and the attachment of the lug angle to the member shall be capable of developing 40% in excess of that force. So we have to design the lug angle in such a way that it can, means it can develop 20% more strength, so that it can carry 20% more, and the lug angle to the angle member shall be capable of 40% more. We will be clear, this will be clear when we will go through one example. We will details, we will discuss all this. Okay. Another thing is, lug angles connecting a channel shaped member shall as far as possible be disposed symmetrically with respect to the section of the member. So this is important. When lug angles connecting a channel shaped member shall as far as possible be disposed symmetrically with respect to the section of the member. This is another provision. Other provision is, in the case of channel members and the like, the lug angles and their connections to the gusset or other supporting member shall be capable of developing a strength not less than 10% in excess of force not accounted for by the direct connection of the member, and the attachment of the lug angles to the member shall be capable of developing 20% in excess of the force. So, in case of channel section, this percentage of excess force which should be able to bear by the lug angle should be 10% and in between 20%. So, in case of angle section it was 20 and 40, and in no case shall fewer than 2 bolts or rivets be used for attaching the lug angle to the gusset plate or other supporting members. That means, minimum 2 number of rivets or 2 number of bolts are required to attach the lug angle with the main member or with the gusset plate. So, that has to be also remember while designing the lug angle. Another thing is the effective connection of the lug angle shall as far as possible terminate at the end of the member connected, and the fastening of the lug angle to the member shall preferably start in advance of the direct connection of the member to the gusset or other supporting member. This is also important. And where lug angles are used to connect an angle member, the whole area of the member shall be taken as effective. Therefore, the net area can be calculated as gross area minus deduction for hole. So, net area we can find out A net as A gross minus deduction of hole. Deduction of hole means n number, suppose n number of hole are there, n into d into t, this will be the whole area. So, n into d into t. So, A gross minus whole area means if number of holes are n, number of rivets are n, and the diameter of rivets is d and t is the thickness of the plate, then net area will be this. So, in this way we have to calculate. Now, with all these provisions, it will be clear if we go through one example. Means here the example has been made so that the provisions given in the code can be followed, and how to design the lug angle and why it is required, in what cases it is required, that will be understood if we go through this example. So, what is this example? That a tension member carrying a load of 200 kilonewton has to connect through a gusset plate of 12 millimeter thick using 60 mm diameter power driven shop rivets. The available length of gusset plate for making connection is 250 millimeter. Design the member and its connection. So, what is the different from the other example? Other example means in previous lecture we have shown one example. So, what is difference here? Difference is this restriction, that the gusset plate for making connection is restricted to 250 millimeter length. Available length of gusset plate is 250 millimeter. So, when we go for solution, we have to see that what are the things are given. First is the tensile force P is given, this is 200 kilonewton, and second thing is the gusset plate thickness of the gusset plate, that is given 12 mm, and rivet diameter is 16 mm power driven shop rivets. Diameter of rivets which will be used for the connection is 60 mm power driven shop rivets, and length of gusset plate is restricted to 250 millimeter. So, these are the things which has been given. Now, we have to design the member, right. So, let us see how to design. Means first what we will do? First we will design the member, then we will design the connections. So first we will go for the design of member. This is the first thing we have to. So first we know axial tensile stress which is given, tensile stress. If it is not given, we have to assume the type of steel which we are going to use. So if we use the mild steel, then 0.6 Fy. So this will become 0.6 into 250. For mild steel, Fy is 250, so this is 150 MPa. So this is given, you can say. Now we can find out the required net area, A net. That will be basically P by sigma AT. So P is given as 200 kilonewton. So 200 kilonewton means, if we make Newton, we have to multiply with 10 cube, and sigma AT is nothing but the permissible stress, which is 150, right. This is permissible axial tensile stress. So after calculating, we will get the area as 1333.33 millimeters square. So now gross area we can find out. Gross area will be, so in case of angle, as we have told earlier, that it is around 40% more than the net area because of deduction of hole and other things. So we have to take gross area little more, that is 20 to 40%. So let us take 40%. So this will become 1.5 into net area is this one. So this will become 1867 millimeter square. So gross area is required 1867 millimeter square. Now what we will do? Now we will go through the table given in the SP6, that handbook 1964, where the properties of angle section and other sections are given. So from there we will find out a suitable section. We need the gross area as this. So if we go through the angle section table, we will see, if we use ISA say 100 by 100 by 10, then we will be getting more or less nearer to that area 1867. So for this, area is becoming 1903, which is closer to this one. So we have to find out the closer section having area nearer to 1867, but not less than this. So the nearer means closer section we are getting as ISA 100 by 100 by 10. So let us try with ISA 100 by 100 by 8. With this angle we will try. So area is coming 1903 millimeter square. Now from the table also we will get minimum radius of gyration. Minimum radius of gyration, which is given in the table, that is 19.4 millimeter. This is required to check the slenderness ratio, whether it is more or less than the slenderness ratio we have to check. And another thing is, we have to find out the gross area, means gross diameter of rivet, because we are going to use rivet as 16 mm diameter. So 16 plus 1.5, which is 17.5 millimeter. So gross diameter of rivet also we have calculated. Now this will be required for connections. So these are the things which require in later we have calculated. Now area of outstanding leg, because you have to find out the net area, then area of outstanding leg, which is called A2. A2 will become 100 minus thickness is 10, so area will be becoming as 950 millimeter square. So area of outstanding lake, which is denoted in general A2, this will become 100 minus thickness into thickness, so this will become 950 millimeter square. Similarly, area of connected lake, which is denoted as A1, this will become 100 minus 17.5 is the gross diameter minus thickness is 10 into 10. So this will become 775 millimeter square. So we got value of A1 and also value of A2. So with this we can find out the value of K1. K1 is basically we know 3A1 by 3A1 plus A2. So the coefficient can be find out now, 3A1 by 3 plus A2. A2 is 950. So plus 950 we can add. So this is coming after calculation as 0.71. Okay. So the coefficient K1 we got as 0.71. Now the net area. Net area we know that will be A1 plus K1 A2. So if we put the values, this will become A1 plus K1 is 0.71 into A2 is 950. So after calculating, this is becoming 1449.5 millimeter square. So net area A net is becoming 1449.5 millimeter square, right. So net area which is less than the required area, sorry, this is greater than the required net area, which is 1333.33. So what we are seeing, that net area is means available net area is greater than the required net area. So it is okay. Now the strength of the member also we can calculate. Strength of member, this will be, so 150 means sigma 80 into net area. Net area available is 1449.5. So this is becoming 217 into 10 cube Newton. That means 217 kilonewton. Now the applied load was 200 kilonewton. So applied load was 200 kilonewton and strength of the member is 217 kilonewton. So this is completely safe. That means the angle section whatever we have chosen, which is ISA 100 by 100 by 10 is okay. So the section whatever we have chosen is completely okay, right. So in this way we can design. Now what we will do? Now we will go for connection design. Design of connection. Member design is over, so we will go for connection design. So for connections, first we have to see what is the strength of the rivet, that means rivet value. So first is strength of rivet in single shear. First we will see strength of rivet in single shear and then bearing, then whichever will be lesser will be the rivet value. So strength of rivet in single shear will be, that is tau Vf into pi by 4 into d square. That means we are using power driven soft rivets, that means tau Vf will become 100 and pi by 4, and we are using 16 mm diameter of rivet, so 17.5. Okay. So this will, after calculating this will become 24.05 kilonewton, right. So rivet value in single shear is 24.05 kilonewton. Now strength in bearing also we have to find out, strength of rivet in bearing. This can be calculated from this formula, sigma Pf into d into T. Now sigma Pf is the bearing stress is 300 for power driven shop rivet, and diameter, gross diameter of the rivet is 17.5, and thickness is given as 10 mm because angle we have chosen 10 mm thickness. So this, after calculating this is becoming 52.5 into 10 cube Newton, that means 52.5 kilonewton. Okay, so rivet value in single shear is 24.05 kilonewton and rivet value in bearing is 52.5 kilonewton. That means we can find out the rivet value, means we can consider the rivet value as lesser of these two, that means 24.05 kilonewton. So rivet value we obtain now. Now we can find out the number of rivets required to bear the load of 200 kilonewton. So 200 kilonewton by 24.05. So this is becoming 8.3. That means around 9 number of rivets will be required to bear 200 kilonewton load for as tensile force. Okay, so number of rivets are becoming 9. Okay, now we have to place in properly this now 9 number of rivets. So for placing this we have to see length of gusset plate required, because the length of gusset plate is restricted. So we have to see whether it can take that much or not, because length of gusset plate was 250. Available length of gusset plate is given as 250 millimeter. So whether it can adjust all the rivets here or not, that we have to check. Now to place the rivets we need the pitch. So minimum pitch we know as 2.5D. So 2.5 into 16 is the diameter of the rivet. So this is 40 millimeter. So minimum pitch at least we have to provide 40 millimeter, and minimum edge distance which is required as per the Coral profession. Minimum edge will be for 16 mm diameter of rivet, that is for this case it will be 25, which is given in the code. So 25 millimeter. Therefore to place 9 rivets the length required will be, means minimum length we should say, because you can use more also. Minimum length which is required will be 8 into 40 plus 2 into 25, because if 9 rivets are placed, so 1, 2, 3, 4, 5, 6, 7, 8, 9. So this pitch distance will be 8, means 8 into this one. Okay, so this will be 8 into 40 plus this edge distance to 25, here 25. So 8 into 40 plus 2 into 25. So this is becoming 370 millimeter, which is greater than 250 millimeter, right. So what we are seeing here, that minimum requirement of length of gusset plate is 370 millimeter, where the available length of gusset plate is given as 250 millimeter. Therefore we cannot place all the rivets here. That is why the lag angle is required. I think now it is understood that why lag angle we have to provide, because providing lag angle we have several disadvantages, like chances of eccentricity, it cannot transfer the load properly. So there are lot of problem is there. Still why we are going for lag angle? Because the restriction of the length of the gusset plate in any case. If the restriction of gusset plate is there, then only we can provide lag angle as an alternative, right. So, now let us provide the lag angle. So, if we have to provide the lag angle, we have to design the lag angle. So, now the thing has come about the lag angle, that as per the codal provision how to design the lag angle we will see. Okay. So, now gross area of connected leg of the main angle section we have to calculate, that is 100 minus 10 by 2 into 10, that is 950 millimeter square. Okay. Why we are calculating? We have to see the sharing of load between two length. Okay. So, area of connected leg is 950. Similarly, gross area of unconnected leg of main angle, that means outstanding leg, this also will become 100 minus 10 by 2 into 10, that is 950. So, sharing will be basically 950 by 950 plus 950, that means 0.5 0.5. That means as the angle is equal, means equal length, that is why 0.5 0.5 means half of distribution will be there. However, for unequal length this distribution will be different, and in that case distribution has to make in that way. Sometimes it may be 0.6 0.4 means 60%, 40%, 30%, 70%, 45%, 55%, whatever it is coming. So, on that basis, on that ratio we have to provide, means we have to calculate the load, and accordingly load will be distributed to the different angle. One will be distributed to the connected leg, another will be, rest will be to the outstanding leg. So, load shared by outstanding leg, this will be how much? 200 kilonewton is the total leg. So, load share will be, that is 200 into 0.5, so 100 kilonewton. Okay. Similarly, load on another leg will be, so load shared by connected leg, that will be also 200 into 0.5, so is equal to 100 kilonewton, right. Now, we will see load on lag angle, how much it is, load on lag angle. So, what we told in the, means what we have studied in the case of this clause 8.8 which is given, that is that in clause 8.8 it was given that 20% load will be, means 20% extra load has to be considered for the lag angle. So, 1.2 into 100. So, load on lag angle will become 120 kilonewton, right. So, this is basically given in the clause 8.8.2 of IS 800 1984. Okay. In this clause it is given that 20% extra load should be able to carried by the lag angle. That is why when we will design the lag angle, we will design for not for 100 kilonewton, but for 1.2 into 100 means 120 kilonewton, right. So, to carry this 120 kilonewton load, the net area required A net, this will be how much? P by sigma it is 150 So, this is coming 800 millimeter square. Okay. So, 800 millimeter square is required. Now, we will see the code, that SP6 handbook. From there we will find out a suitable angle. So, let use say ISA 70 by 70 by 8, where the area is becoming 1058, right. We need area of 800 millimeter square and we are providing nearer to that, which is 1058. Basically, we will see which one is the closer value, means which area is coming to closer to 800 millimeter, but it should not be in any case less than 800 millimeter, right. So, if we choose 70 by 70 by 8, this area has this much. So, we can think about that, and of course, we have to see what is the net area. So, net area will be this minus 8 into 17.5, right. So, because this is the deduction of hole, thinking that 16 mm power driven shop rivet is used and one rivet in each line it has been used. So, net area will become this much, this is coming around 900 millimeter square, which is greater than the area required. So, this is okay. That is why we have taken little more, because the net area required is 800 millimeter square. Now, after deducting the whole area, means after deducting whole, the net area should become more than 800 or at least 800. So, after deducting we are getting 900 millimeter square. So, that is why we can consider that this section 70 by 70 by 8 is okay. Now, we have to find out the number of rivets for connecting lug angle. So, for connecting lug angles, first we have to find out the number of rivets, and before finding out the number of rivets we have to know what is the rivet value. So, rivet value means rivet value in shear, single shear, and rivet value in bearing. So, rivet value in bearing, how much it is coming? This will be sigma Pf into D into T. So, sigma Pf is for power driven shop rivet, this is 300, D is 17.5 the gross diameter of the rivet, and thickness of the angle is 8. So, this is coming, and by 10 cube to make it kilonewton. So, this is coming 42 kilonewton. This is strength of rivet in bearing. Similarly, rivet value in single shear, this will become tau Vf into pi by 4 into d square, that means 100 into pi by 4 into d means 17.5 square, and to make it kilonewton you have to divide by 1000. So, this is coming around 24.05 kilonewton. So, now, so the rivet value will become lesser of these two. So, rivet value which is denoted as R, this will become 24.05 kilonewton, right. So, rivet value we are getting now. Okay. And now, we can find out the number of rivets required. So, number of rivets required, this will become, number of rivets will be how much? That is 1.4 into 100, 40% extra has to be made by 24.05. Okay. So, that is becoming 5.8, that means 6 number of rivets will be required for this. So, number of rivets required to connect this as 6. Again, number of rivet required to connect lug angle with gusset plate, that is 20% extra, that means 1.2 into 100 by 24.05, this is coming 4.99, that means 5. So, observe this, that number of rivets required to connect lug angle with gusset plate is 5 and number of rivets required to connect lug angle with main member is 6, that means 40%. So, for one case it is 40%, another case for gusset plate it is 20% and for main member it is 40%, right. So, that is why here we are multiplying with 1.4 and there we are multiplying with 1.2. So, we are getting number of rivets which connects the lug angle with the main member is 6 and lug angle with the gusset plate is going to become 5. Okay. Now, we have to distribute properly. Say minimum first, minimum pitch will be 2.5 D, that means 2.5 into 16, this is becoming 40 mm, right, and minimum edge distance, minimum edge will become 25 mm as per the codal provision. So, from this we can provide this minimum, or as we have sufficient length, so let us provide pitch, as say 50 mm and edge distance as say 40 mm. Okay. With this we can distribute the rivets properly. Okay. Another thing is number of rivets required to connect main angle with gusset plate, that also we have to find out. Number of rivets required to connect main angle with gusset plate. Here also we are providing same diameter of rivets, so this will become 100 by, because 100 kilonewton load is transferring to through this gusset plate and the main angle, that is 100 by 24.505 kilonewton. So, this is becoming 4.15, that means this is also 5. Okay. So, 3 interface is there, one is gusset plate with main member, another is main member with lug angle, another is lug angle with gusset plate, right. So, 3 interfaces are there. So, if we draw, then I think it will be clear, right. Let us draw the and make the details. So, this is the angle, right, and this angle section is 100 by 100 by 10. So, and here is the gusset plate is there, again the lug angle has been provided here, right. So, lug angle is there, then this is the gusset plate. So, this is 12 mm thick gusset plate, this is one. Second thing is this is ISA 100 by 100 by 10, the section of the angle, the main angle is 100 by 100 by 10. Now, the main angle is connected to the gusset plate with a number of 5. So, 1, 2, 3, 4, 5. 5 numbers of rivets are there. Okay. And the lug angle and the gusset plate having also 5 numbers. So, we can make 1, 2, 3, 4, 5, and the number of rivets between the main angle and the lug angle are 6 as we got. So, this will become so 6, right. Now, these are basically 5 number of 16/5 PDS power difference of rivets, so at 50 mm center to center. Okay. This is the distribution, and here this is 5 number of 16/5 PDS at 50 millimeter center to center, and here this is 6 number of 16 PDS at 50 millimeter center to center, right. So, in this way we can make it. Now, let us see the length of gusset plate required to make this. Length of gusset plate will be required, that is we have 5 number, that means 4 into 50 plus 2 into 40. So, this is coming 280, right, and we have in fact 250, total length was 250. So, which is not okay. So, what we can do now, we can reduce the pitch. So, if we reduce the pitch to 40, I think we can make it. So, 40 and let us make the edge as 30. So, in that case 160 plus 70, that means 230, which is less than 250. So, the pitch let us make for this one as 40. Pitch which is connected to the gusset plate, let us make 40, and edge let us make 30 to include that 5 number of gusset plate, 5 number of rivets into the gusset plate. So, we can redesign, means reorient the rivets, so that the required length which is given 250 millimeter for the gusset plate can be adjusted in this. So, in this way we can make. Otherwise, if we want to provide the pitch say 50 and edge say 40, then again we have to redesign it, means we have to go for another sort of rivet, so that number of rivet become less, so that we can place properly, right. So, in this way I think we are in this way we can design the lag angle. So, what I told in the beginning of design of lag angle is that lag angle is necessary when the length of gusset plate is restricted. So, in that case, to accommodate that many number of rivets for high load, heavier load, we have to go for lag angle, providing extra plate, angle type plate, extra plate with additional to gusset plate, and design considerations as given in the clause 8.8 of IS 800 1984, we have to follow those things and accordingly we have to design. Okay. Another thing is tension splice. So, when tension splice is necessary, basically when the size of member changes at different lengths. That means, if a member is like this and another member is say suppose like this. So, in that case, so this is your member 1, say member 2 and member 1. Okay. Now, here we need some tension splice. Another thing is when members are connected through butt joint, if the size of member, thickness of member is same also, then also it is required if it is butt joint, and when the length of section available is less than that of tension member required. In this case also the tension splice is required, and when the two type of member thickness has to be connected, to fill up the gap we need another extra material which is called packing. Okay, this is called packing. So, packing is necessary to fill up the gap when members of different thickness are spliced. Members of different thickness are spliced, in that case packing is necessary. So, here the codal provision is that additional number of rivets need to be provided in the extension of the packing having more than 6 mm thickness by 2.5% for each 2 mm thickness of packing. So, this is the codal provision which has been given. That means, extra rivet is required to make the packing by that 2.5% if the thickness is more than 6 mm. For each 2 mm thickness, 2.5% extra will be required. So, in this way we have to calculate. Now, I think this will be clear if we go through the example, means when we will go through the example, how the rivet is required for packing also will be understood, right. So, now let us go through this example. So, design a tension splice to connect two tension member of 200 by 10 and 250 by 18 millimeter. The member is subjected to a pull of P is equal to say 250 kilonewton and use say 20 mm diameter of power driven sub rivet. So, what to do? That design a tension splice to connect two tension member. The member size is 200 by 10 and 250 by 18 mm and the force acting on that member is 250 kilonewton tensile force. Now, use 20 millimeter diameter of power driven sub rivets. So, with this let us design the tension splice. So, what we will do for the solution? First we will find out the strength of rivets. Okay. Strength of rivets in double shear. I am coming why double shear is required. So, this will be 2 into tau Vf into pi by 4 d square. So, this will become 72.61 kilonewton. This is 100 and this d will be 21.5. Okay. So, after putting this value we will get 72.61 kilonewton. Now, why it is required? Because when these two members are spliced, say here one packing is given, then we need to, this is the tension splice, okay, splice. Okay. So, when the rivets are providing here, what we are going to get? Rivets are under double shear. So, that is why strength of rivets in double shear we have calculated. Now, strength of rivet in bearing, so that will become sigma Pf into d into T. So, 300 into d is 21.5, T is the thinner part of the plate, one is 18 mm thickness, another is 10 mm thickness. So, the lower one we will see, this is 10 mm and this is 18 mm.
I am using what I am going to do. I am using this. What you are telling?
So, strength of rivet in bearing is becoming this. So, after calculating this we will get 64.5 Newton, that means 64.5 kilonewton, right. So, the rivet value we can find out as the minimum of these two, one is 64.5 kilonewton, another is we got here 72.61 kilonewton. So, minimum of these two will become 64.5 kilonewton, right. So, rivet value we have. Now, what we will do? Number of rivets. So, number of rivets n will become the load was 250 kilonewton by 64.5. So this will become 3.1 or equal to 4. So number of rivets we are getting 4, right. Now thickness of packing. So what will be the thickness of packing? Because we have to see this is 18 millimeter and this is 10 millimeter. So thickness of packing will become 8 millimeter, 18 minus 10. So thickness of packing will become 8 millimeter. Okay. So additional rivets necessary for each 2 mm thickness of packing as per the codal provision, that is 2.5% for each 2 mm packing. So 8 mm was the packing thickness, so 8 by 2, okay, that means 10%. So additional rivets will be required 10%. So that means number of rivets was 4. So additional rivet will become how many? Additional rivet will become 10% of 4 rivet, that means 0.4, that means 1. Okay. So total number of rivet will become how much? That will be 4 plus 1. 4 is to join the tension splice and 1 is for packing. So total number of rivets are 5. Okay. So 4 number of rivets will be required in the splice and 1 will be required in the extension of packing, and I will show in the figure. Now pitch will be 2.5 D. So 2.5 into D is 20, so that is 50 millimeter. Okay. Pitch we can consider as 50, right. Now another thing is, so minimum pitch is 50, so let us make say 60 millimeter pitch, so provide 60 millimeter. Okay. And now the thing is that we have to find out the thickness of tension splice, thickness of splice plate. Okay. There is 2 ways we can calculate the thickness of tension splice. One is, let us assume and we will check whether the splice can take that much load or not. First we will assume that, say let thickness of splice plate as say 10 mm on both sides. Okay. 10 mm was the thickness of the plate also, so that is why let us consider say 10 mm on both sides. That means if we provide both sides tension splice with 10 mm, then strength will become strength of splice plate at critical section will be how much? 2 into 150 by 1000 is for kilonewton, 200 is the width. So if we consider thickness of width of splice as the 200 millimeter, which is given in the one plate, if we consider accordingly, then 200 and minus 2 into 21.5, this is the diameter of the rivet. If we consider that the 2 rivets are in a section, it is given, so this into 10 mm thickness. So if we provide, this is becoming 471 kilonewton, which is greater than 250 kilonewton. That means the tension splice thickness, whatever we have considered, is okay. Okay. So tension splice we have considered 10 mm thickness, and in fact the width we have considered 200 mm width. So 200 by 10 is sufficient to carry this much. In other way also we can find out the thickness of the tension splice. That is that we can assume let thickness is equal to T, we do not know. Okay. So if thickness is T, then strength of splice will become 2 into 150 by 10 cube into 200 minus 2 into 21.5 into T, and this has to become 250 because the strength of the tension splice has to become equal to the applied load, which is 250. That means tension splice should carry the load which is applied in the member, that is 250 kilonewton. So if we make equal, we will get T as 5.3 millimeter. That means we can use 6 mm. Okay. Hence we can provide in place of 10 mm 6 mm thick tension splice can be provided. Okay. Hence provide 6 mm thick tension splice in both sides. Okay. So in this way you can make it. So both the way you can find out, either we can assume the thickness of the tensile splice and then we can check whether it is okay or not, otherwise we can make it equilibrium, that make it equal to the applied force which is equal to the strength of the tension splice. From that we can find out the thickness, right. Now if we draw the figure, means if we see the diagram how it look like, let us see. So this will be, this is main plate, this is another plate, this is the packing, right. Now tension splice we are giving one here, another here. Okay. So this is the tension splice. Okay. This is a tension splice, this is packing. Okay. So this is 8 mm packing, this is 10 mm or 6 mm, say we are providing 6 mm splice. Okay. This is also 6 mm splice, and this is 18 mm and this is 10 mm, right. Now if we see in the plan, we will see another is so if we see in the plan, this is basically 250 millimeter and this is 200 millimeter, this was 200 millimeter, right. And so now rivets will be, basically we will provide rivets, this is one here, one here, one and another extra here. So we will get like this, say 4 rivets are here and like this it will go on, and one another extra will be here, this is there. Okay. So 25 PDS at 60 mm center to center. So in this way we can, in the plan the splice how it has been made can be seen. Okay. And in the side view, if we see the splicer, one splicer provided at top and one splicer provided at bottom with same thickness of 6 mm thickness, right. So this is the way how to design the splice. Okay. Tension splice, why it is required and how to design, all this I think it is clear through this example. Okay. Now with this I like to conclude today's lecture. Thank you.